Good morning, everybody. Y'all doing okay? Had a good break, I trust. We went to Hattiesburg. Did I tell y'all we were going to Hattiesburg? Have I seen y'all since the break? Oh, yeah, I saw y'all last Thursday. Well, never mind. We're not going to talk about that. That's okay. That's fine. We are going to have our quiz today. Remember that quiz is going to cover that last part of Chapter 2. And then we'll be having Chapter 3 quiz. I'll send an email out about this, probably on Tuesday. All right. So a week from today, Chapter 3. And it'll cover all of Chapter 3. It's good to have as many quizzes as we can. I think it's good practice for y'all. They don't really count a whole lot. I mean, they're not insignificant, but the more quizzes we get, that means the more that you get dropped. So anything over 5, we're going to drop. I know that I'll guarantee you one drop quiz, but hopefully we'll get more than that. Okay? Any news today to report? What's the news? Thanks, Stacy. Okay. Let's try these questions. So we just have a couple more, and then we're going to carry on and talk about kinetic energy. In a baseball game, the catcher stops a 90-mile-an-hour pitch. What can you say about the work done by the catcher on the ball? So the work is doing a certain amount of work on the ball. He's applying a force to the ball. What type of work is that? Positive, negative, or zero work? No, this is chapter 3. Yeah, you missed chapter 3. Yeah, you can talk to one another. All right, I'll stop at 110. About 6 more seconds. Just guess if you don't know. Just a few more seconds. All right. Okay, very good. The catcher has done negative work. We'll talk about this. And in general, we're going to talk about how work is related to energy. Have we already done that? How work is related to energy? No, we're going to discuss that. But the way that we've talked about work now, the catcher is exerting a force on the ball in that direction, but the ball is traveling in this direction. So that's a negative work. Whenever your force opposes the direction of motion, that's negative work. So B is the right answer here. A ball is tied to a string being whirled around as a circle. What can you say about the work done by tension? So I twirl a string around my head with a ball on the end. The tension in the rope is pulling this ball into a circular path. What is the work done by tension? And you want to ask yourself, what is the relationship between, the geometrical relationship between the displacement, or the direction that it's traveling, and the force? And that should give you some hint as to what the work being done is. Remember our cosines. We had cosine 0, 90, and 180. Cosine of 0 is 1, cosine of 90 is 0, and cosine of 180 is negative 1. Morning, ladies. Come on in. All right, I'll stop 10 more seconds, 135. So just guess if you don't know. 135, 5 seconds. Okay, we're all over the board. Let me draw a picture of this right now. So I have a guy, and he's twirling a string over his head, and there's a ball, and this thing is going back and forth like this. All right, what is the direction of the displacement? Let's say that it's going in this direction. At this particular point, what is the direction that the ball is moving at this instant? Is it moving to the left, right, into the page, or out of the page, right here? No, it's moving out of the page. Like, think 3D. Okay, so over here, it's going in this direction. But what is the direction of the force? Left, right, or out of the page, or into the page? No, the force, see this tension right here, is pulling the ball in this direction. So my displacement is out of the page, but my force, the tension force, is in this direction. But my displacement is out of the page. Is coming towards you. It's like the ball is moving towards you. So let's try that again. Now that you know that the tension force is to the right and the displacement is out of the page, what then is the work being done by this tension force? All right, I'll stop at 45. 45. I think we're a little bit better here. And so A is the right answer. Because those force and the displacement is perpendicular, they're separated by an angle of 90 degrees. The cosine of 90 is 0, and so it does no work at all. It does no work. Good job, the 15 of you. So we're going to talk about next how work actually changes the energy. And the fact is that this tension force does nothing to change the energy of the ball. That tension actually, all it does is it changes the direction of the ball. Okay. And that's where we'll stop for now. We'll come back to some of these other questions later. All right. One other thing. Did I mention the food drive to y'all last Thursday? Okay, so the food drive, Nichols Can is a food drive. Have y'all heard of Nichols Can? Yeah, it's going to go, I think, through the 26th of this month. And, Nichols has really become a big contributor to the food bank here in Thibodaux. And I think it's a really great opportunity for us, as a campus, to contribute to people that don't have much. I mean, I know that most of us come from, even if we're just sort of middle or even lower class, we come from pretty wealthy families, all in all. And that every time we sit down to the table, we have food to eat. That's true for almost all of us. I know it's not true for all of us, but for most of us, it is true. And so by giving to things like the food bank, we're able to help people that don't have money for a meal, for example. And so as a class, we're going to participate in this way. Normally, I don't like to give extra credit for things that aren't associated with the class, but I think this is a good cause, and it's really a way for us to help others that are in need. What we're going to do is that I'll send an email out detailing all the numbers, is that each of you will bring in, say, 5 items. That can be canned food items, dry good items like rice or whatever. It can also be, and they really need this, like hygiene items like toothbrushes, toothpaste, that kind of thing that you can't buy with the SNAP cards, the food stamp cards. So those types of things are really needed. Baby items, you sort of know what I mean, right? Items. They can't be expired, so if you bring food items, they need to be unexpired and they need to be unopened in order for the food bank to take them. So as a class, and not just y'all, but includes all of my classes, I will give you a certain number of points for every amount of cans that you bring in. I haven't worked the numbers yet, but it's going to work something like this. Say if I have 100 students, no, let's say I have 200 students, which is pretty close. I have about 200 students. If each of those people bring in 5 cans, then we'll get 1,000 items, right? And so I'll give you 1 point for every 100 items that we bring in. That means if every student brings in 5 items, we'll get we'll get 1,000 items, but you'll get 10 points. And that 10 points will sort of go into the pool Right? So you can add it to a quiz, you can add it to an exam, whatever. Doesn't matter. It just sort of goes into the pot. For your class, it accounts for a couple, 2 or 3 percentage points. So it's not insignificant, but it's not a whole lot either. Okay? Is that clear what I mean? I'll send an email out soon, today or before the end of the week, just outlining this and reminding you. But you'll need to bring those items to me, and then I'll mark it down like, well, yeah, Physics 151, they brought in this many cans. It's not individual, it's corporate, what we're doing. So it's as a whole group. So either the class gets it or the class doesn't get it. And you don't have to get the total 10 points. Like if you bring in 800 items, for example, you'll just get 8 points. Or if you bring in 850 items, you'll get 8 points. Yeah. Well, every student individually will get the 10 points, right? But it depends upon the total amount of food items that are brought in from all the classes together. So the 1,000 cans will include from all the students. So if this class brings in nothing, but Physics 102 or whatever, they bring in 1,000 items, then y'all still benefit. That's not going to happen, obviously, but if that did happen, that would be the way it works. Okay? All right, good. I think it's a really great way, as I said, to help people that are in need. And Nichols, we've really become a big contributor. I think last year, it gets bigger every year, but last year we gave something like 15,000 items to the food bank, including a large monetary donation. By the way, if you'd rather give money, I don't like handling money, but you can make, if you want to give money, you can make out a check to the Nichols Foundation and just put Nichols Can Drive. Just talk to me if you want to do that. That's fine. And it is tax deductible if that worries you. All right? Okay. Let's see. So we're going to move on now to energy, and we'll see a close relationship between work and energy. Listen, the reason we're doing all this is to help us develop this idea of how energy is used and how energy is used to do work. And so obviously that's going to have applications when we get into the body, because the body takes in food energy and produces work by that. And so later we'll talk about the metabolism of the body and how the body uses this food energy to produce work. But first we need sort of a basic understanding of what energy is and what work is. Now energy, we're going to have lots of different types of energy that we'll talk about. But one of the primary types of energy is kinetic energy. Now y'all know what kinetic means, right? Like kinesiology, that's the same root, is the study of what? Motion, right. So kinetic energy is the energy of motion. So anytime an object moves, it has kinetic energy. The kinetic energy we can calculate. There aren't many formulas here, but there are a few, and this is one of them that you need to know. The kinetic energy is equal to 1/2 m times v squared, where m is the mass. And obviously we're going to use the SI system. And in the SI system, the mass, the unit for mass is what? Kilograms, right. Yeah, we use the kilogram for mass. And velocity, or rather this is the speed, which is going to be in meters per second. And then the units for energy, the units for kinetic energy, are the joule. It's lowercase, joule. 1 joule is equal to 1 kilogram meter per second squared. Meter squared per second squared. I just do that by plugging in these basic SI units into this equation. I have kilograms, I have meters per second squared. And so that gives me the basic SI units of a joule, which is 1 kilogram meter squared per second squared. All right? Now if you do work on an object, then you change its kinetic energy, or you change its energy in particular. Give y'all just a second, I'll move on. I can go on? All right. So if you do work on an object, remember whenever I say work, I mean that work equals F times D. or F times D cosine theta. If you do work on an object, you change its energy. And this is where those signs become really important. If you're doing positive work, remember positive work was F and D are in the same direction. If you do positive work, you increase the energy of the object. I'm going to abbreviate energy as an E. All right, so positive work causes an increase of the energy, and the opposite of this is also true. Negative work, that means that F and D are in opposite directions, as we've seen. So if I have a force in this direction, but my object is moving in this direction, that's negative work. Like the catcher catching the ball, he's applying a force in that direction, but the ball is moving in this direction, that's negative work. And if you do negative work, the energy of the object decreases. And in fact, the amount of work that you do is equal to the change in the energy. This is called something we call the WorkEnergy Theorem. It has a lot of applications. And in physics, I mean, we don't work a whole lot of complicated problems, but in physics, this idea makes working a number of different physical problems a lot easier. The WorkEnergy Theorem, and it just says that the work is equal to the change in energy. If I do work, I cause a change in energy. It basically equates this work and energy. Anytime I do work, I'm using up energy. Or anytime I'm gaining energy, I'm gaining the ability to do work. If I eat, a bag full of potato chips or whatever, I'm gaining the ability to go out and hit a home run or whatever. That's probably not a good example, but you get the idea, okay? That this energy can be used to do work. All right, let's try a question. Let's say that I push a car at constant velocity. What is the total work done? All right, is the total work A, positive, B, negative, or C, 0? What is the total work done? Positive, negative, or 0? I push a car at constant velocity. What is the total work done? The total work done on the car. Let's add that. Let me remind you of something about total work done on an object. The total work done is equal to the net force times the displacement. Right now, most of you have the answer wrong. Just want to let you know. The total work is equal to the net force on the object times the displacement. Okay, that's a little better. Right? What is the net force on this car moving at a constant speed? That was a rhetorical question. All right. Looks like almost all of you have gotten rid of option B, and you're split pretty evenly between option A and C. B is not the correct answer, so which is it? Is it positive work or zero work? All right, I'll stop at 2:05. Okay, C is the right answer here. I have zero work done because the net force on the car is equal to zero. Because I have the force that I'm pushing on with, but something that's not stated in this car is, well, not the gravitational force, but what force is it? I have the frictional force. The frictional force is opposing you, it's pushing in the opposite direction, or whatever force it is, like your brother that doesn't want to go to school. You remember that? You push back in the opposite direction to keep your car from getting to school. And so the net force here is zero. But I can understand why you would put positive. What is a good argument for putting positive? It's in motion, right? And that's a good reasoning, right? Because the velocity it is moving, and so it has energy, right? But the total work done here at this point is still zero. But we know, however, that at some point, some amount of work must have been done, right? To accelerate that car up to a constant speed. So there has been work done on the car in the past that has increased its energy, but once it gets that energy, that work has now leveled off and it's now zero. So remember, our work is not equal to the kinetic energy, or is not equal to the total energy, rather. So I wrote it before. Our work is equal to the change in energy. So work results in a change in energy, not necessarily in the energy that the object has. Destiny? Yeah, so if the car was accelerating, that would mean that the net force would be something greater than zero. Like if you're pushing on the accelerator and you're causing the engine to turn more and causing the wheels to turn at a greater rate, then yes, it would be positive work. If it was accelerating, it would be positive work. But if it was accelerating, you'd also be increasing the velocity and hence also increasing the energy. Right? But here you're not changing the energy. Okay? So A is the incorrect answer, but it's a good incorrect answer because it does have energy, but work is equal to the change in energy, not in the total energy. Yeah. So? Right. The total amount of work that's being done on the object is zero. Now you can break this down. When we talk about systems, and we'll talk about sort of closed and open systems, but you can break it down and say, well, the person pushing the car is doing positive work, but the friction is doing negative work. But when you add those two together, that goes to zero. All right? We'll talk about that in a little bit. That becomes an important topic, open and closed systems. And in fact, you can make your system bigger and bigger and bigger until you have the whole universe. And then if you have the whole universe, the network done in the whole universe is going to be what? It's going to be zero. Right. So we'll talk about that later. All right, let's ask another question. Which, just sort of to quiz you, which of these is a unit of work? Which of these, I'm going to give you some units, is a unit of work? Which of these is a unit of work? And also remember that this is going to be the same as a unit of energy. So I could ask either one of these, which is a unit of work or which is a unit of energy, and those answers would be the same. Work and energy are the same. Remember your expression for work, and that'll tell you what the units are. You just put in the units for each thing. Looks like we're split, not evenly, but we're split between A and C. So I'm going to go ahead and get rid of B and D. All right, B and D aren't options. You can choose between A or C. All right, I'll stop at 120. 120. Okay, very good. E wasn't an option. A is the right answer. Work is force times displacement, and so force is newtons, displacement is meters. But also the point here that I want to make is that 1 Newton meter, which is the unit for work, is equal to 1 joule, which is the unit for energy, because they're the same, basically. And that's equal to our basic SI units, are kilogram meter squared per second squared. You can see this because, remember, energy is 1/2 m v squared. That is m as in kilograms, v squared as in meter squared per second squared. And if you recall, the unit for newtons was kilograms meters per second squared times meters. And notice that this unit, which is the basic SI units for work, is also the same as that basic SI units for energy. They're the same, is the point, that the units for work and the units for energy are the same, and for a good reason. Well, while I say that work and energy are the same, that's not exactly right. But it is sort of true, too, that if I do work, I cause a change in the energy. And so the units are going to be the same. So we'll talk about work and energy to be very closely related. Okay? There's another type of energy. And by the way, I'm planning we'll stop at 10 and I'll give you a quiz and then you can take your quiz. It probably won't take 20 minutes, but I'll give you the full 20 minutes. Okay, next type of energy is potential energy. There are lots of different types of potential energy. Chemical potential energy, elastic potential energy, but the one that we'll deal with first is called gravitational potential energy. Just in general, we're going to call potential energy U. So we'll use this variable. And so U, which is potential energy, is stored energy or you can think of it as the capability to do work. Oh, I forgot to bring a rubber band. I'm sorry. I'll try to bring it next time. So I got a rubber band and I stretch it out. It has the ability to do work, right? What happens if I let go of it? It shoots you in the eye and you go blind for the rest of your life, right? But so if I have something that has the ability to do work, then I call that potential energy. Or also, like, for example, we'll talk about gravitational potential energy. If I have this and I hold it a certain distance from the Earth, it has the potential for energy. It has potential energy. It has the potential for motion, because if I let it go, it falls, right, because of the Earth's gravitational force. So U is stored energy or the capability to do work. We'll also talk about chemical energy, which is a type of potential energy, and our bodies use chemical energy. Food is a type of stored energy that we'll discuss. So there are many different types of potential energy. There is elastic, like the rubber band. There's gravitational potential energy. That is, the paper clip holding a certain distance from the Earth. It has a potential for motion if you drop it. Chemical energy is a type of potential energy. For example, food energy. And then electric potential energy, which hopefully we'll get to. by the end of the semester. But I have no agenda. We'll just sort of get where we get. And actually, chemical energy is closely related to electric potential energy. Electric potential energy says if I have two charges and I bring them close together, then they're going to have the potential for motion. You'll probably have this in third grade or whatever. If I have two like charges, two positive charges, they're going to do what? They're going to fly apart, right? And so they have a certain amount of energy. They have this energy for motion. And so we talk about electric potential energy. And this electric potential energy, this is the reason that we have chemical energy, because you have the molecules that make up the food or whatever chemical it is that you have, and they contain a certain amount of potential energy just because of the configuration of the charged particles that make up the molecules or the atoms. All right, so let's say that I move an object. I take an object and I move it from here at h equals 0, and I move it up to here to a height h. I apply a certain force and I move it from this point, from the initial point, this is my beginning, to the ending point. I want to know how much work has been done. What work has been done to move this block? And once you answer that question, you will also answer the question of what amount of potential energy does it have. So what work has been done to move this block? So I'm asking that you apply a force to move the block from the top to the bottom. I'm not asking the total work. I'm asking you apply a force to move it from one point to another. And I want to know what work has been done to move it. We'll take option A as mg over h. B, F over h. C, and D. All right, so try that out. What work is done to move this block? Moving the block from h equals 0, the ground level, up to some height. I want to know the work that's been done to move it. All right, just a few more seconds. I'll stop at 55. 55. Have I told y'all the roast beef joke? But have I told y'all that roast beef pea soup joke? No, you weren't here if you didn't hear it. Let's see, I have a list. I keep a list. Y'all want to? Oh, here's a good one. Oh, y'all gonna like this one. Uh, why can't you hear pterodactyls when they go to the bathroom? Because the P is silent. Because y'all did so well on this one. C is the right answer. Remember, work is just force times displacement. I'm applying a force to this block. That force has to equal the weight of the block to move it, and I bring it up to a height h, and so the total amount of work then has to be mgh. And as I told you, if you did that, then you have now derived the expression for gravitational potential energy, which is going to be m times g times h. So this is the amount of gravitational potential energy, gravitational potential energy that an object has. It's just the mass of the object times g times h. Remember, g here is equal to 10 meters per second squared, mgh. The units, of course, for this are what? The unit for energy is the joule, right. So the unit for this is the joule. And just to show you, remember we said that the basic SI unit for energy is a kilogram meter squared per second squared. That was the units for kinetic energy, that 1 joule is equal to this. Notice that we also have the same here. M is in kilograms, G is in meters per second squared, and then H is in meters. So those are the same units. Gravitational potential energy has the same units as kinetic energy has the same units as work. All right? So that's an expression that you'll just need to know. Now, when you take this object, my favorite clip, I'll use this. When I take an object and I take it from h equals 0 and I move it and I do so many joules of work, right? I do so many joules of work in moving it. When I release the object, what happens to that potential energy? It becomes kinetic energy. So like as I release it, here it has less potential energy, but it has more kinetic energy. And then as it goes all the way to the floor, at the floor it has no potential energy, but right before it hits the floor, it has a significant amount of kinetic energy. All right, we'll get to that. That's called the conservation of energy, the law of conservation of energy. Don't write that down now. We'll see it later. But right now I want to watch a little video. This is a PBS series that they put out. It was like a reality show about circuses. Have y'all seen this? Well, when PBS makes reality shows, like they're different from like the Lindsay Lohan type reality shows on television. But this one is actually pretty good and interesting. And they made a series of clips that have to do with physics and the physics of the circus. So I recommend the full show. You can find it online. Let's watch it now. If you want, I know that some of you can probably do this. And like if you choose not to do a review, a paper review, like a written review, at the end of the semester you can do that, 5 to 7 minute presentation or whatever, and then you could do this and you could talk about conservation of energy. And that would be cool. Wouldn't it be neat? All right. Okay, so we'll get into this conservation of energy. Do you think that it would help in this class if I wore a clown nose like that fella? And a cool suit? No, it wouldn't help. Okay, so there are other types of energy. Other types of energy. It's going to sort of go through them, and it'll probably take us up to our quiz, maybe. First, there's mechanical energy. Mechanical energy. And mechanical energy, when we talk about mechanical energy, it's really just the sum of the kinetic, K, and the gravitational potential energy, or the potential energy. We have the conservation of mechanical energy. Which the clown on the video talked about. The conservation of mechanical energy, which just basically says that energy always remains constant. So like in the video with the acrobat, she had 3 different types of energy, one of which was kinetic, and then she had 2 different types of potential energy. What were the 2 different types of potential energy? Elastic and gravitational. So she had gravitational potential energy, and then in the bar, whenever she came down, the bar would bend, and that would store quite a bit of energy, and she uses that energy to her benefit to throw her up into the air. So that total amount of energy remains the same. It's just converted back and forth between kinetic and potential energy. All right? So E remains constant. Or energy transforms, rather. I'm sorry. Energy transforms from one type to another, from kinetic to potential, but the total amount remains constant. The total amount being the sum of K plus U remains constant. Right, so if K, for example, goes up, that means that U has to decrease by the same amount. If K goes up by 10 joules, U decreases by 10 joules. I go down from here. Okay. All right, so let's consider this. Let's consider I have a roller coaster. Oh, let me redraw that. All right, wait until I get it drawn completely before you draw it. Say that I have a roller coaster that looks like this, and I have a cart that is here. It sits some height above the ground. It's moving with a certain velocity, and it travels all throughout here until it comes up here and it stops. All right? Where is the kinetic energy greatest? I'm going to label some points, and then I'll ask you a few questions. I'll label this as point A, this is point B, this is point C, and up here I'll call this point D. So the first question I want to ask is, where is the kinetic energy greatest? Where is the kinetic energy greatest? At A, B, C, or D? Right? Most of you are putting B or C right now. One of those is correct. I'll stop at 50 seconds. B is correct. I have a total amount of energy. That energy is equal to K plus U. All right, the point where the potential energy is least is where the kinetic energy is greatest. Let me ask you here, where is the potential energy least? If you're listening, you should get this pretty quickly. Where is the potential energy least? Where has the least value for the gravitational potential energy? You're about evenly split between B and C here, okay? And one of those is correct. Between B and C. Where is the potential energy least? Remember our potential energy, U, is equal to mgh. And I want to know, where is that least? Most of you are wrong, in fact, but it is either B or C. So think about, where is the potential energy the least value? All right, I'll stop about 135. Think about your answer. 5 more seconds. 135. Okay. What's the right answer? Who's the most confident? It's B, right. So you see people like you weren't sure, were you? Like you weren't real sure about it? Yeah, B is the right answer. Because that's where H equals 0. What is my potential energy at that point? At B. It has no potential energy at all. So it's at point B, and that's where H equals 0. So that's where the potential energy is at its least value. And likewise, that's also where the kinetic energy is at its greatest value. So it's the same answer for 1 and 2. All right, one more question. Where is the kinetic energy least? Which point, A, B, C, or D, has the least amount of kinetic energy? All right, I'll stop at 45, so about 6 more seconds. Okay, very good. D is the right answer. In fact, if it comes to a stop up here, which I think is what I said, but it doesn't matter whether it comes to a stop or not, this is still where it has the least kinetic energy, and simply because it has the most potential energy up there. So if it has the most potential energy, that means that K has to decrease by a similar amount. All right, let's do one more quick thing, and then I'll give you your quiz. Can I come away from this? I'm going to work through a quick little problem. Just want to show you how we might use this in a problem. Bless you. I suspect problems on your exam, though, would be more conceptual like this. I'll have to think about that, and I'll let you know if you would have numerical problems. But I want to work through a numerical problem just so you can see how simple it is. I have a little video, and I like this video, so let's show it. That is a real video or not, that's beside the point. I have this simple problem that I can address. So I have this young lady, and she goes up into the air, and then she comes back down. She goes to a basketball hoop. Well, that's much bigger than it looks. Much smaller than I've drawn it, actually. And I want to know what is her velocity here. All right? I know that at the bottom that she has no potential energy and that she has all kinetic energy. And that kinetic energy is 1/2 mv squared. And I know up at the top that she has no kinetic energy because when you throw her up in the air at the very top, she's at rest for just a moment before turning around and coming back down again. We saw that with the acrobat in the circus. And when she went up, she was at rest for just a moment before coming back down again. And the potential energy is equal to m times g times h. But we know from the law of conservation of energy that these two have to be equal. So my initial energy has to equal my final energy because this conservation mechanical energy says that this has to always remain constant. And so at the bottom, that's going to be 1/2 mv squared plus 0. And at the top, it's going to be 0 plus mgh. And so obviously the zeros just go away. I just wrote them as placeholders. And I get 1/2 mv squared equals mgh. The masses cancel if I divide both sides by the mass. And I solve for v. I multiply both sides by 2. Take the square root of both sides. And I get v is equal to the square root of 2 times g times h. So it becomes a very simple problem to determine what is her initial velocity. So all we really need to know is what is her height. How high does she go, do you think? Basketball goal is how many feet? Is 10 feet. That's roughly 3 meters. So how high does she go? 15 feet, you think? Okay, so that's roughly what? 5 meters, right? So we'll say 5 meters then. So that's square root of 2 times 10 times 5. Well, those are nice numbers because that's the square root of 100 or 10 meters per second. 10 meters per second is actually pretty fast. What is that approximately? I think that's about 20 or 30 miles an hour, if I'm not mistaken. All right. Why don't we go ahead and stop there, and we'll give you a quiz. Any questions, though? Okay, I'll leave it up for a sec. What did I say?